Hello everyone, I'm Jiahui Hu from George Sikis Group in AM/PM Center. I'm gonna share my work which applied machine learning for performance prediction of membrane separations. Before starting our story, let's discuss why it's necessary to combine AI and OSM membranes. Membrane is a selective barrier between two phases and is impermeable or semi-permeable to specific molecules when exposed to a driving force. Nowadays, due to environmental regulations, chemical and pharmaceutical industries are required to enhance their existing high energy consumption separation processes, including distillation and evaporation. OSM membrane technology is a promising method to replace them due to its sustainability and less energy demand process. However, membrane screening processes are trial and error. Moreover, process distribution in membrane cannot be controlled easily, which leads to unpredictable separation performance. Therefore, we pursue new pathways to develop OSM membrane. Instead of doing tedious lab work, establishing predictive models assists OSM membrane development. In general, there are two methods. The first one is to construct models based on thermodynamic or transport phenomenon calculations. However, these models cannot predict performance of membrane in general systems. The second one is to build models by collecting large database. The diagram below demonstrates an AI-guided OSM membrane development process that we used. After knowing our motivations, I would like to discuss the methodology of this work. We collected data from literature followed by data treatment. Then we have applied this pre-treated data to build AI models. Due to time limitation, I will mainly focus on data verification in the following slides. In this work, we applied three machine learning algorithms. They are ANN, SVM, and RF. The first two are for membrane performance prediction, while RF is a data classification model in our case. Next, let's look at the results. Our target is to predict membrane separation performance, which is determined by two variables, permeance and rejection. Permeance measures how fast the solvent penetrates the membrane, while rejection discloses the selectivity to tested compounds. Let's look at the results given by ANN model. The top two figures compare experimental and predicted results for permeance, while the bottom two are for rejection. The horizontal and vertical axes describe experimental and predicted results, respectively. We applied 70% of pre-treated data to train the model, 50% data to validate the model, and the rest 15% was to test the model. R-square value obtained from test and train sets are above 0.9, which means the goodness of fitting function can represent most of data nicely. Additionally, we calculated the deviation of R-square between test and train set. The differences is roughly 0.07 for both cases. Similar procedures were performed on SVM algorithm. From the table, we can say that the deviation of R-square between test and train set in SVM model is smaller than in ANN model. Therefore, we conclude that SVM model is more suitable for our collected data. In conclusion, by combining AI and OSM membrane, it may be able to address challenging problem of membrane scaling up. Our proposed method provides a broader horizon to study OSM membrane data and serves as a guide to decrease OSM membrane screening time that fast-tracks the industrial implementation of OSM membrane. At last, I want to thank the researchers who contributed and helped me in this project. Thank you all, and also thank you to this conference, which provide me a valuable opportunity to share my work with you.